Good evening, everyone. Today I'm going to give the presentation on the topic Inelastic Electron Tunneling Spectroscopy. So let's start the presentation. Contents. The contents includes the introduction, history and discovery, quantum tunneling, working principle, experimental setup and instrumentation, mechanism of inelastic electron tunneling spectroscopy, the features, that is first derivative and second derivative, the advantages and the disadvantages, the applications and the research paper. So let's go through the introduction part. So inelastic electron tunneling spectroscopy is a powerful method that is basically used to analyze the vibrational modes and the electronic characteristics of molecules and surfaces in detail. IATS is based on the concept of quantum tunneling, where electrons move through an insulating layer that has been sandwiched between two metal electrodes. A thin insulating layer here acts as a barrier which is made up of oxide layer that is being sandwiched between the two metal electrodes. Now in this diagram we can see an oxide layer that is being sandwiched between the two metal electrodes, and this whole system acts as a tunnel junction which uh, which is responsible for the flow of electrons and also act as a barrier for the flow of electrons. This insulating layer prevents direct electrical conduction between the conductor. Now, this oxide layer is made up of either aluminum oxide or magnesium oxide or other oxide layers such as silicon oxide or niobium oxide. Now, the aluminum oxide. The aluminum oxide is used basically because of its stability and ease of formation. And magnesium oxide is used where high tunneling barrier height is required. Now, over here, the metal electrodes are made up of either platinum, gold, aluminium, or silver. The gold is used because it is chemically inert and resistant to oxidation, which makes it excellent choice for stable and reproducible electrode. Also, other electrodes such as niobium is used for specialized ITS studies involving superconducting states. Let's go through the history and discovery. In 1966, scientists J. Lambe and R.C. Chekilwick at Ford Research Laboratories discovered the phenomena of inelastic electron tunneling. They were studying electron tunneling in metal insulator metal junctions and observed that the tunneling current had features related to the vibrational modes of molecules adsorbed on the insulating layer. Their discovery was groundbreaking because it showed that the electron tunneling could excite vibrational modes of adsorbed molecules, producing specific measurable signatures in the tunneling current. This provided a way to analyze molecular vibrations on the surface in manner similar to infrared spectroscopy but with much higher intensity. Historically, IITS was first applied for the studies of molecular vibrations in thin oxide films, but it quickly gained broader relevance. Now, today it is used in fields such as nanotechnology, surface chemistry, and molecular electronics. IITs can probe single molecular junctions and nanostructures with remarkable sensitivity, making it a valuable tool for investigating phenomena like electron-phonon coupling. Also, its high resolutions and non-destructive nature can make it a suitable for characterizing complex systems without altering their structure. Now let's study what is quantum tunneling. Basically, quantum tunneling is defined as a quantum mechanical process in which the wave function can penetrate through the potential barrier. Now let's assume that an electron is approaching the potential barrier. Now, according to classical mechanics, if the kinetic energy E of the electron is less than the height of the potential barrier, that is h, then the electron would not cross the potential barrier. Instead, it would strike the potential barrier and get reflected back in the opposite direction. Now, In quantum mechanics, the situation is different due to the wave-like nature of the particle. When an electron approaches the barrier, its wave function doesn't stop at the barrier. Instead, it decays into the barrier and allows the small part of the barrier, a small part of it to pass through the barrier. Now, if the barrier is neither infinitely tall nor infinitely wide, then according to quantum mechanics, there is finite probability of the electron appearing on the other side of the barrier. That means if the electron, even it doesn't have that much of classical energy to cross the barrier, but according to quantum mechanics, it would jump over the barrier or it would tunnel through the barrier and would continue its path on the other side of the barrier. Now, wave function and probability. So, in quantum mechanics, particles are described by wave functions, which provide a probability distribution of where a particle might be. When an electron, for instance, encounters a barrier, its wave function extends into the barrier, while the amplitude of the wave function decreases or decays inside the barrier. It doesn't drop to zero unless the barrier is infinitely thin. If the barrier is thin enough, if the wave function on the other side of the barrier has a non-zero amplitude, meaning there's a small chance that an electron can tunnel through the barrier and appear on the other side, even without the required classical energy. As I have said in the previous slide, even if the classical energy of the electron is not that much that it would overcome the barrier, but it has a finite probability that it can tunnel through the barrier and continue its path on the other side of the barrier. Now let's go through the working principle. Now, in a tunnel junction, we have two electronically conducting materials, that is either metals or semiconductors, which are being separated by an extremely thin insulating layer, which is basically around 10 to 30 angstrom thick. Now, this setup somewhat acts like a capacitor, which prevents the direct conduction between the metals. However, when an electron wave function from one metal overlaps with that of the other uh, metal across the insulating layer, then the electron tunneling can occur. This means that even without a direct path, electrons can still tunnel from one side to the other due to the quantum mechanical effect. Now, when we apply a voltage across the junction, it drives a current that induces two types of contribution. Therefore, two types of tunneling. That is the elastic tunneling and inelastic tunneling. In elastic tunneling, the electron passes through the barrier without losing any energy. But in elastic tunneling, some electrons loses its energy by interacting with vibration in the material or with adsorbed molecules on the insulating layer. Now, the experimental setup and instrumentation. In inelastic electron tunneling spectroscopy, the setup is designed to study the tunneling of electrons through a barrier while capturing both elastic and inelastic processes. This requires specialized equipment to create tunnel junctions, measure current voltage characteristics, and detect inelastic tunneling events. Below is an explanation of the experimental setup, focusing on tunnel junctions and measurement apart. Basically, the experimental setup and instrumentation consist of two parts, that is the tunnel junction part and the measurement apparatus part. So let's go through the tunnel junction part first. A tunnel junction is the core or the heart of IET's experiment. It consists of a narrow insulating layer between two conducting materials. Electrodes are injected from one conductor, often a metal tip, through the insulating barrier to a second conductor, typically a substrate or a sample surface. The barrier can be either a metal insulator metal junction or a molecular tunnel junction. In metal insulator metal junction, a metallic tip is brought near a conducting substrate with an insulating layer in between. Now, in molecular tunnel junction, a molecule or a thin layer of material is sandwiched between two electrodes with an electron tunneling through a molecular layer. Types of tunnel junction in IEDs. The first junction is the STM junction, that is scanning tunneling microscope. The scanning tunneling microscopy is a powerful technique that allows for atomic level imaging and measurement of conductive surfaces. The STM junction is formed between a conductive tip and the sample surfaces, with a small and a control gap between them. In an STM, a very sharp conductive metal tip is brought extremely close to the surface of a conductive sample, and a bias voltage is applied between the tip and the surface. When the distance is small enough, electrons can tunnel across the gap between the tip and the sample. This tunneling current is highly sensitive to the tip sample distance, varying exponentially with even the slightest change in the gap. This allows for incredible precision in measuring surface topography. Now, the second type of tunnel junction is the break junction. The break junctions are created by mechanically stretching a thin metal wire until it breaks, forming a narrow gap between the two broken ends. These are often used to study quantum transport in atomic scale systems. Let's study about the mechanism of break junction. In a break junction setup, a thin metallic wire is placed between two electrodes. The wire is then pulled or stretched under controlled conditions until it narrows to an atomic scale, eventually breaking. After breaking, a gap forms and the tunneling junction is created between the broken ends. The gap size can be controlled by finely adjusting the stretching. Now, this gap allows the electron to tunnel between the two ends, and the conductance of this junction can be measured as a function of the gap distance and the applied voltage. Now, the third junction. The third junction is the molecular junctions. The molecular junctions are created by placing individual molecules between two conductive materials. These are used to investigate the quantum mechanical properties of single molecules, such as conduction, conductance, vibrational states, and interactions with their environment. Let's study about the mechanism of molecular junction. In a molecular junction, a single molecule is sandwiched between the two metal electrodes, creating a nanoscale bridge. The junction is typically created in two ways, either by directly positioning the molecule between the electrode, like that in scanning tunneling microscopy, or by using break junction techniques where molecules naturally form a bridge after breaking. When a bias voltage is applied between the electrodes, the electrons can tunnel through the molecule. In some cases, the molecule's own electronic structures and vibrational modes significantly influences the tunneling current. Let's go to the second part of the experimental setup, that is the measurement apparatus. The measurement apparatus consists of parts. That is, the first part is the lock-in amplifier, the second is the voltage control, the third is the electron junction spectroscopy, the fourth is the thermocouple and the temperature control, the fifth is the electron transfer pathway, the sixth is the data acquisition system, the seventh is the oscilloscope display, the eighth one is the sample chamber, and ninth one is the Veltor. Now let's study about their functions. So the miscellaneous part. The miscellaneous parts includes the clock and hourglass, which represents the time-related aspects, which defines the stability of the system over time and collects the data over the time intervals for a long duration experiment. The second one is the Well-Thomsey and Accordec Tunwell Junsiopy. that is the additional control. The function of this is to appear for the additional knobs or settings, perhaps for fine tuning the voltage or current levels to ensure precise measurements during spectroscopic analysis. Here is the schematic representation of the IETS setup. In this, we can see the lock-in allot allot tune, that is also known as lock-in amplifier. Basically, a lock-in amplifier is used to improve the signal to noise ratio by isolating the desired frequency of the tunneling current from background noise, allowing for clearer detection of inelastic tunneling events. The second one is the voltage and the voltaic altime, that is also known as voltage control device. Therefore, its function is to control the voltage by adjusting the bias voltage across the tunnel junction, allowing for precise control over the energy of electrons. This is crucial for sweeping through voltage ranges to detect energy levels of vibration modes. The fourth one is the electron junction spectroscopy, that is also electron junction spectroscopy. Its function, uh, its function is to interact with the vibration modes of the sample. The equipment includes control or visualization tools to interpret tunneling events. The fifth one is the thermocouple and the temperature control. The temperature control and the measurements are essential in IETS to ensure stable conditions and prevent thermal noise from affecting the tunneling current measurement. This part might symbolize a thermocouple or a cooling element. Now, the electron transfer pathway. Its function is to label and represent the electron pathway through the junction, where the inelastic tunneling events occurs. It illustrates the flow of electron as they pass through the sample. The last one is the data acquisition system. A data acquisition system collects the tunneling current data and uh, and records variations as the voltage changes. This information is then passed to produce IETS spectra showing vibrational peaks. The mechanism of inelastic electron tunneling. The mechanism includes the energy transfer and inelastic scattering events. In inelastic electron tunneling, an electron transfers part of its energy to the material by passing through it. This energy loss can excite certain vibration modes within the material, like phonons, which are vibrations of atom in a lattice, or other specific molecular vibrations. As a result, this energy transfer acts like a signature that reflects the energy levels of these vibrations. By analyzing these signatures, scientists can learn about the material or molecules involved. The second is the role of threshold voltage. In inelastic tunneling starts at a specific threshold voltage, which represents the minimum energy needed for an electron to excite a particular vibration mode in material. Once the applied voltage hits this threshold, some electrons begin to tunnel inelastically, causing a slight increase in the overall conductance. This increase signals the beginning of inelastic tunneling. The threshold voltage is important because it directly reflects the energy of the material's vibrational modes. By studying changes in the conductance at these voltages, we can map out of these energies level and gain insights into the material properties. The first derivative. The first derivative tells us about how the applied voltage changes with the current. It represents the conductance of a system, which is a measure of how the current flows into the system. The second derivative. The second derivative of the current with respect to voltage represents the rate of change of conductance. This derivative helps to highlight sharp features in IV curve that might be less obvious in the first derivatives. It also helps in identification of energy levels and also in helps in noise reduction. The advantages. The first advantages is the extreme sensitivity. The IITs can detect subtle energy changes that are associated with molecular vibrations, making it a very sensitive to small molecular changes. The second is adaptable to a wide range of molecules. IIT is adapted to wide range of molecules, offering flexibility in study of different samples. The third advantage is the temperature programmable. IIT's instrument can operate at various temperatures, allowing for control measurements and reduce thermal noise, especially at low temperatures. The fourth one is the good resolution. The IETs provides high spectral resolutions, enabling the identification of fine vibrational features. The fifth one is no selection rules. Unlike some other spectroscopic techniques, IITs do not have strict selection rules, meaning it can detect vibrations regardless of symmetry or dipole charges. Disadvantages. The first disadvantage is that artificial environments are required. IIT's experiments often need control environments, such as vacuum chambers, to prevent interference from external factors like air molecules. The second disadvantage is expensive. The IIT's setup equipments are very costly, making it less accessible for some research facilities. The third one is that it requires cryogenic facilities. IITs typically operates at extremely low temperatures that are the cryogenic that that are also known as the cryogenic conditions to reduce thermal noise, necessitating specialized cryogenic equipment that are very costly. Let's go through the applications. The first application is the characterization of molecular vibrations. The second is the molecular electronics and junctions. The third application is the characterization of nanostructures and nanomaterials. The fourth application is surface science and catalysis. The fifth application is superconductivity and phonon-electron interactions. The fifth application is biology, surface physics. The seventh application is trace and parity detection. The eighth application is metal molecule interaction, and the ninth application is adhesion. Thank you.